finite field, prime field, is here, 530 bit. So this has been by Klein-Jung in APFL. In those days, he was still in Bonn, Germany, and so the idea is he proposed new polynomial selection, so technique, and he improved also something. Then so it becomes so. So there is a jump here. In the case of so extension field of medium size, so we have some result after proposing so the idea in crypto and Eurocrypt. And currently this is the top record, 676 bit. Yeah, I show you this slide, the current top record. As I said, for the prime field, Klein-Jung, so 530 bit, about 1 month. Using many CPUs, they have not specified so how many CPUs they use. And in the case of characteristic 2, so 613 in 17 days, and so on. Here, so in the case of P to the 30, in this case, so 556, quite large, in just so 12 hours. But in this case, so P to the 30 has a very special property. We can make the constant very small. Therefore, so this can be done just half day. And so in the case of so 3 to the 6th, this type of finite field is particularly important for pairing-based cryptography. Today, I don't so explain a lot about pairing-based cryptography. So pairing-based cryptography uses this type of very special so characteristic and so extension. And here 6 and 3 so should be combined together. And so this record has been done in our group and with the help of government and so on. And so in Japan, so we had some discussion, pairing cryptography is practical or not. And we are very interested to bring it practice. And so they said, is this field is secure or not? We should estimate so the security of this finite field by considering recent new development of theory and so hardware and software. And so we did this project. So we cannot compare these problems in one situation, but so currently it is the largest record. And so NICT is a Japanese government organization which supports cryptographic research. They offered us in total 96 CPU cores, and so we use this machine. And so why we choose 96? So of course there's a limit of budget, so what they can pay. And so 96 is not so small, not so large, it's the middle level. And so it costs about, I forgot the money, but $100,000 US or so to buy these machines. Then so we say, okay, we say this is $1,000 US. And what can we do? Then so if we invest more, and what can we do? So by analyzing this size of experiment, we can expect what's happened in the near future. It is our goal. For example, let's say 660 bit. So takes 1 year with $1 million US. It is the current top record. And so this line shows the asymptotic estimation by theory. And here's log scale. And so, for example, let's say, we make 10% larger than current bit size. Then the speed or time or cost could become 5 times more. Okay. It means from 600 bit we make 660 bit. So we need from 1 million to 5 million. Of course, reality is not so easy to estimate, but we know some estimation here. Okay, we make the bit size 50% larger, from 600 bit to 900 bit. Then it takes about 2,374 times longer. Okay, it is 1 year to, here scale is a little different, so some mistake here. So I compute it here, so then it becomes about 2,000 times more. It means 2,000 years. Then we know, so how much should we, how many bits should we make larger for future? Okay, and then attacker, how many US dollars they should investigate, and so on. But so this is just so estimated by current state of the art of technologies. What is important is we have Moore's law. Maybe you know that. So every 18 months, so CPU or computer becomes twice faster. There are many different statements, but it means the speed of CPU is exponentially fast. Nowadays it seems not, but we cannot say 15% longer could not be safe in next decade or in long-term estimation. Then we should always keep investigating the current record. Why? So how many CPU or how many GPU or how many money for cloud computing and so on. Then we know maybe just next 10 years or so. Okay. So we have 15 minutes more. Yeah?
Does it over right for
10 minutes break? Okay. Yeah. Okay. 10 minutes break. Here. In this case, Gordon first proposed 93 first adaptation of number field to EM problem. Then Shirokawa enhanced the constant term here. So 9/64 to the 1/3. And Julian here proposed some practical improvement. And currently in this case is the most fastest in practice. Therefore, I want to use this for comparison. And what I wrote here is a low Hamming rate. What is low Hamming rate? Low Hamming rate is means in the following. P is represented by signed binary like this. Namely, the number of non-zero bit is W. And non-zero bit means the coefficient of the signed binary is +1 or -1. And delta becomes 0 if we don't we don't count if the digit is 0. So here delta is just 1 to the delta W. this is a signed representation of weight W. And so this kind of prime is quite important for cryptography. For example, when you look at NIST prime, it is equal to, for example, P equal to 2 to the 60 plus 2 to the 30 minus 1, like that. It has only 3 non-zero bits. And so low Hamming weight has been often used for efficient implementation of cryptography. And so, interestingly, Shirakawa proposed an efficient variation of number field sieve 2006. He said, we can achieve this asymptotic speed. And theta is equal to this number. For example, W is equal to 2 means 2 times 2, 4 minus 3, and 2 minus 1. It means theta is equal to 1. It's a minimum case, 1. Here's 1. Then it is faster than this previous number field C. Yeah. And W is enough large, and so it becomes 2. Then, if we substitute 2 here, then it's equal to normal, number field C. This means the variation of by Shirakawa becomes particularly faster for the small Hamming weight. And so it is a very interesting observation here. Some cryptographers want to use small Hamming weight, prime number, but there is this attack. And so indeed, for example, pairing-based cryptography, we are using so-called BN curves, and many papers deal with small Hamming weight. In such a case, this attack is quite in some sense dangerous. We should think again, descale the security parameter by considering this attack. Okay, what we want to do in this talk is we want to compare this standard number field sieve and new number field sieve. In this talk we say JL03 NFS and Shirakawa 06 NFS. Yes? So we don't specify here, but in our experiment we implemented less than 6. Less than 6. W equal.
Is that the low Hamming weight that pairing-based curves?
So in pairing-based cryptography, they use Hamming weight is for example 20, and so it depends on paper. So some paper is extremely small, no Hamming weight. So some, for example, 5 or so. But so currently fastest implementation use 20 for 256 bit. It depends on also size of P. And so my goal is to estimate such a efficient, estimate the security of it. Efficient pairing. It is a final goal. So now just this is preliminary work. Okay. So number field sieve consists of 4 steps. First, polynomial selection, and searching relation, linear algebra, and individual logarithm. So linear algebra, it's same as the index calculus method, and also searching relation is also same to the individual logarithm case. And here is new. So we have to generate appropriate polynomial, because we use number field. Then we need to define polynomial used for number field. And so this selection is quite different in both cases. So Shirokawa 06 and so JL 03. And so we mainly explain how the polynomial selection are different. And in general, so this individual logarithm case is very efficient. So I want to say that it is less than 1% of whole number field sieve. Therefore, in this implementation, we discard this part. So we mainly implement this first 3 steps. Okay, let's see the polynomial selection for JL03. We use these 2 polynomials. This is degree n plus 1 polynomial. This is degree n. And so we won't say n is just very small. So for example, 1, 2, 3. So maybe we use at most 4, maybe smaller. So for example, if we choose 1, this is degree 2 polynomial. This is degree 1 polynomial. And so F1 and F2 are reducible over the rational fields. And so point is here, both polynomials have a common root p, modulo p. And so and so most important part is here. The size of polynomial depends on the speed of number field, sieve. And the trick achieved by JL03 is to choose very small coefficient for the polynomial 1. Here, just small constant. For example, 2, 3, 5, and so on. Very small one. And here, the other polynomial has also small coefficient like this. C1 equal to P1 over n plus 1. Okay? And so these 2 polynomials can be generated by LLL deductions. So for given polynomial f1, we compute n root of polynomial f1. Then we perform LLL, which has a common root of f1. So by LLL, we found such a small coefficient polynomial. So reduced base, equivalent to the coefficient. And this step is very efficient, just a few seconds. Okay. And from now, I explain how to use these polynomials for number field sieve. Let N1, NB be degree of polynomial f1 and f2. Here we use n1 equal to n plus 1, n2 equal to n. Then we compute the complex root of here f1 and f2. Both have different root. It's a common root, modulo p, but we have a different root in the complex field. And so this root can define number field. So we say for alpha 1 is k1 and alpha 2 is k2. And so this number field has an integer ring 1 and O2. Okay, this is standard integer ring. Number field sieve use some orders included in the integer ring here, z alpha 1 and z alpha 2. Just we adjoining just alpha 1 here. And in some case this z alpha 1 is exactly equal to 1, but in some case not. If this is a proper so order of maximal order. In that case, we have some problem in number field sieve. It is called butterflies. Such a butterflies is very difficult to deal with, and so we need some complicated mathematics, Kumma-Dedekind theorem or other very classical number field techniques here. And anyway, here we number field sieve use Z alpha and Z alpha 2. And the point of number field sieve is we generate two different copies of finite field. Namely, we consider ring homomorphism from Z alpha 1 to finite field, GFP, and another homomorphism here, Z alpha 2 to GFP. And so this maps from alpha 1 to n, alpha 2 to n. Same, embedded. If n is same, therefore we need the same, here, common root here. It means now we have, instead of GP, we have more huge area to deal with this problem. So this is a kind of two different liftings. And the idea is in index calculus method, we use small prime numbers in integers. But now we can use prime ideal decomposition of small node. Instead of prime, we want to use prime ideal here. Okay. Now, this is a polynomial selection for Shirakawa O6. So this polynomial selection uses two polynomials. First one is just x minus n. Of course, this has root, m, f1 x equal to 0. The other one is calculated a little complicated way. I explain here. And the point is first property and second property are same here. And the point is n here, n here is relatively small, not much small than as much as JLO3 case, but here relatively small. And here coefficient Ci is very small in many cases. It is point here. And size of coefficient Ci is estimated like this. It's depending on two parameters, E and gamma. And in some case very small, in some case not, but relatively small. So how we compute E and gamma? Here a little complicated, very technical. So I quickly explain, but not I go to details. Here we have a signed binary representation of the prime characteristic T. And so at first we compute E. E is delta W is the highest exponent. We divide by n. N is the order and the degree of polynomial. And for example, in cryptographic purposes, for example, this is, for example, 256, and n is 5, like that. Then, we compute delta I modulo E. We assign it as di, and we reorder this di for I equal to w in the size of here like this. Of course, the highest size is E, and smallest could be 0, and like this. Then, what is gamma? Gamma is a maximum distance to adjacent di and di plus 1. Sometimes, so di is concentrated on some region. In that case, so this gamma becomes very large. Then, so coefficient becomes small. It depends on the distribution of the exponent here. It means so even we have large Hamming weight, this gamma is so large enough, we can accelerate the speed. On the other hand, so even Hamming weight is small, sometimes very slow, because so gamma is small. Therefore, it depends on so primes. Okay. Now, so I want to explain so the common phase so for searching. This is called sometimes seeding phase of number field sieve. How can we so generate many relations using the polynomials? It corresponds to the prime decomposition of index calculus method. The idea is to prepare larger factor base here. In the case of index calculus method, we have only rational factor base. So namely, so factor base, the rational, the out is so rational primes, so smaller than b or equal to b. And here, we prepare two additional factor base, b1 and b2. And so this is algebraic so factor base. What is that? This is so special prime ideal of degree 1, which has this representation. So namely, so this prime ideal is generated by two so numbers. One is rational prime q. That's rational prime in the factor base. Namely, this q is b smooth number. That's smaller than b, y equal to b. And so this second part is a root, complex root of alpha 1 minus t. And so this t satisfies this equation. Namely, so it is a root of f1 equal to 0 modulo q. So as I said, so f1 is so degree 5 or so. Therefore, for one prime q, rational prime q, we could have here several different so t1, t1, t2, t3, and so on, up to the so degree of polynomial f1. Sometimes just one, sometimes so up to 5. Okay, then we prepare same one. In the case of Shokawa 06, so we have degree 1 polynomial. In that case, so b1 is equivalent to fb. This part is degenerated to the rational case. Therefore, in some case, we have rational and algebraic. In some case, we have both algebraic. So we fix C bound B, C, and so we want to gather so pairs, so number B1, number B2, and N1 and N2. This is the degree of so polynomial, and so this is a cardinality of factor base. Then we generate linear algebra. Then how can we so gather such a pairs? So we generate two integers a and b, and a is bounded by c bound, and b is also bounded by c bound c, and so which satisfies so GCD common so greatest divisor is 1. And here's an important point. So 2 here, property 2 means so when we consider so this principal ideal a plus b alpha I, this prime ideal can be decomposed to the so and this principal ideal decomposed to the final ideal of B1. Here is B1, mistake. Here is B2. And so if we have a large prime ideal here, not in the factor base, then we threw it the pair AB. And we do same here, and so this AB must satisfy both property 2 and 3. Therefore, this AB is called a double smooth pair, not only one smooth. This should be satisfy 2 and 3 there. Then, here is the point, here. Actually, this is very complicated to find the prime ideal decomposition in general. It is a part of the study of computational algebraic number theory. It's not easy. And so the way we use in practice is we just use degree 1 prime ideal, and in this case we can prove that the coefficient epsilon here, epsilon, can be computed by the prime decomposition in rational field of the norm here, this number a plus b alpha. Here's a principal ideal, but here we just compute as a number, and so we can compute norm easily by definition polynomial IFI. Then we have a rational number here. Then we can decompose this rational number in the same way of the index calculus method. And if we know this EI, we can easily compute EJI here. How we compute that? It is like this. For example, let's say the exponent is of Q in the norm of alpha plus b, A plus b alpha is epsilon. Then this epsilon is exactly the exponent of this ideal. I said there are several t here, but we can select like this. T equal to just minus a over b modulo q. By checking this equation, we know this epsilon is exactly this one. It means ideal is split several ways in the extension field. But when we see the exponent of the norm, then we can select just one prime ideal in the extension field. It's not divided to part. It's just equal to one of them. And all computation is elementary here. Then we can select which prime is the prime ideal above the rational prime by this equation. Then we know that we can determine this exponent. Okay, and now it can be computed to this. This is also a very simple equation. Okay. Then problem here is more complicated. We want to now map this double smooth equation to the rational case. But then we have some problems because these equations in second or 3 is equal as an ideal. If we want to compute logarithm of the both sides, we have a problem of unit. There's a unit. So if we think it as an integer or as number, there is a unit problem. And so how can we solve the unit problem? It was a very huge problem in number field Sieve for the DL problem. And Shirokawa so elegantly solved this problem. He introduced so-called Shirokawa's character map. I don't explain this a lot in this slide. And so this, using this map, we can remove the ambiguity of units. So this Shirokawa map uses so-called local unit. So this character map can decide the local exponent of the local unit. And so for computing, so for each equations, for adding this Shirokawa's character map, then we can obtain here as an equal modulo L. This is the point. So this Shirokawa character can be efficiently computed. In our experiment, it is less than 3% of whole computation. And now we get one relationship here. And so now we have here logarithm of the prime ideal. Yeah. Then it seems almost goal to find logarithm of rational number. How can we do it? Okay. Before that, we bring everything to the right. Then we write down like this equation. And so to find this logarithm is to find the kernel of the linear system. Then later we want to solve the kernel. And so how can we switch this logarithm to the rational case? Then answer is easy. So we use such as completely split prime. So this is a degree of the number field. Then in some case we have the complete splitting prime here. In that case, by adding logarithm from here to m and j, we can obtain the logarithm of rational number. Yeah, of course here we need some character map in order to avoid the unit problem. And the individual logarithm can be also done in the same manner. We compute prime decomposition, but we know the small we perform this prime decomposition in the rational field, then we know the logarithm for small norm, then we can solve it. So in some case, we have here problem. We have no rational prime because it's not completely splitted. In that case, we can change the base, or we can recompute by randomizing target element or base element. And this step is enough efficient. Okay, now I'll show you the example of matrix generated by here. So let's say P equals 40 bit. This is an example. It's very hard to see. So here's the rational side. And I didn't write the prime number here, but here is the prime 2, exponent of prime 2, prime 3, prime 5, prime 7, 11, and so on. And as you see, it is very sparse, matrix. And also you can see that non-zero bit appears more for small primes here. For large primes, not so, almost zero. And here is the algebraic side. So we compute prime ideal decomposition here. And you also see here is many, so relatively, so many non-zero bit, and here not so much. Then here is a Shirakawa character map. It is as large as 40 bit. And in this case, we are dealing with degree 2. Therefore, we have two maps. And so rational case, we have no maps because it is rational. No ambiguity of the unit. Okay. Then we want to solve the kernel of this matrix. And usually we compute using the Wiedemann or Lanchos method. And so it depends on your platform. So we implemented both Lanchos and Wiedemann, but Lanchos seems better in our experiments. Therefore, we chose Lanchos method. Okay, this is our experiment. So computing is done by Core 2 Duo. RAM is 2 GB, and Linux and C. So we use the compiler, this compiler. And so for the multi-precision arithmetic, we use GMP. And for lattice error detection, we use NTL. And for bat primes, this is this library, RE, is very nice library for computational number theory. We find the exponent of bat primes using this pipe. Then correction operation can be done line C and linear algebra. So uses the Lanchos method. Okay. So in our experiment, we choose 100-bit prime P, whose Hamming weight is equal to 5 or less than 5. And so particularly, we chose that P minus 1 over 2 is also prime. This is Sophie-German prime. In this case, we found 945 such primes. We thought okay. We wanted an experiment of size 1,000 primes. Then in this purpose is enough. Then I chose this prime. And in the case of JL03, we chose degree 2 and 1. In the case of Shirakawa 06, we chose degree 1, and by computing this 3. And for Sieve bound, in the previous report of JL, D equals C, and so this number seems optimal. Therefore, we adapt this number from the previous reference. And so in the case of Shirakawa, Shirakawa suggested this bound, but this is very pessimistic bound, asymptotic. So estimation, this bound is optimal, but in your purpose, not so nice, too large. Therefore, we divide it in some area, and so we try to find the best one in our purpose. And so by 1,000 region, then we try to find the best performance. And so the data I show you next is the best one. And in this case also we change a little, but there is no big difference to change this bound. Therefore, I think both are relatively optimal implementation. Okay, in the case of JL03, we have polynomial. So, for example, x squared for f1, x squared plus 5. And so, the second coefficient is like this. This is 50-bit primes. Okay? So, by computing, in this case, Gaussian reduction is enough, to create this one. more than 2, we need an LLL, but in this case, Gaussian, we completely with Gaussian reduction. And so Shirakawa 0.6, so it's quite different for each primes. I show you here 2 extremely different cases. For M, so Shirakawa proposed to use this one to do this 33. This is fixed loss case. But here, in some case, so even it has a small Hamming weight, this is quite small coefficient, but in this case not. It is depend on the E, modulo E of the exponent, the distribution of the Hamming weight. The position of Hamming weight, so a non-zero bit decides this coefficient. Then we perform on 945 times. Then I show you the histogram here. Then this is the result. In the case of Shirakawa 06, so we have such a keen histogram. It is very concentrated on the one place. So this means very stable, this algorithm. In other words, we cannot optimize a lot now. In the case of JL303, sometimes it's very efficient, but sometimes not efficient. Very much slower than JL03. Indeed, average value is slower than JL03. Yeah. But some primes are faster. It was I expected not this result. It was a little surprising for me to see this distribution. Okay. Now we did more larger bit, and in this case more than 100 bit. In the case of JL03, we choose degree 2, 1, 3, 2. And in the case of Shirakawa, we have some other primes like this, up to 245 or 259 bits in our experiment. And this is the distribution. I chose the fastest in the both case, then we get this distribution. In the fastest case, in Shirakawa, 06, I got here 10 because he published a German version, mass comp, later, therefore I switched here 10. In the fastest case, it's always faster than JL03. Therefore, we should particularly carefully to use such a prime numbers. And I show the fastest case becomes much faster if the bit range becomes large in this slide. For the 150, just 4 times, but 200 bits, 8 times, 200, 59, 18 times faster. And the difference becomes larger. Then what we want to compute is more than 1,000 bit has a much difference. In that case, we should really carefully take such a weak primes of Shirakawa attacks. Okay, we implemented both Shirakawa 06 and JL03 NFS, and variance of timing for Shirakawa is larger than Julian's here, and the fastest case has 4 times, 8 times, 18 times faster. And now we are implementing more than 300 bit, using lattice sieve or other techniques using number field sieve. Then we want to estimate finally security